Welcome back, everybody. What we're going to do right now is finish up talking about Chapter 5. We're going to focus on Section 3. So this is Section 5.3. And what we're going to really focus on is taking our discussion of looking at the normal distribution and computing probability to another level. We're going to take it to the level such that we're starting to learn all that we need to know to compute some basic inferential stats. And in order to get there, we need to learn another really important concept, and that's central limit theorem. So I know this chapter is tough. I know you don't always see the connection for how we're going to be able to use Z-scores and normal distributions for computing inferential stats. But this is an important area. We're learning a bunch of important skills that are going to be needed for computing inferential statistics, even if you don't see that connection today. You just have to trust me. The next chapter that we're going to cover is going to put all this to use, and then you're going to see, oh, okay, that's why I had to learn all this stuff. So everything that we're doing right now is going to lead us right into a discussion of inferential statistics so that we can determine if we have statistically significant results or not. So let's talk about central limit theorem in this particular section. And you'll find in most research studies, we're looking at groups of people. We're not looking at individuals. So we're going to have to extend our conversation because everything that we've been doing so far, we've been looking at individual scores within a distribution. Now we're going to have to figure out not only what's the probability of scoring in some region, but what's the probability that many people would score in some particular region. What if I were to measure many people, compute a group mean, and then figure out what's the probability of finding this group mean just by chance? That's exactly what we're going to need to do with inferential stats. And central limit theorem is the key for making that easy. So let's jump right in. Let's go through kind of an example to set up what I'm talking about. Let's look at IQ scores again. So let's assume that IQ scores form a normal distribution with a mean of 100 and a standard deviation of 16, which is typically the case with IQ scores. Then what's the probability that a group of 100 randomly selected people will have an average IQ over 110? So essentially what we're trying to figure out is what's the probability that some sample mean will be over 110? And we have not yet learned some way to answer this question because what we've looked at before is a distribution of individual scores. We've transformed some individual score into a Z-score and then looked up its probability. We're not dealing with individual scores in this case. Now we're talking about scores that come from 100 randomly selected people, and we've computed an average for those 100 randomly selected people. So we're going to need to now extend our conversation from a distribution of individual scores to what we call a distribution of all possible sample means. And I'm going to make that clear to you what that is in just a few minutes. So a distribution of individual scores allows us to determine the probability of any particular score. That's what we did in our last lecture. But a distribution of sample means is going to allow us to determine the probability of any particular sample mean. All right, well, that's the key distinction right there. And central limit theorem, CLT, is going to help us create that distribution of sample means pretty easily because according to central limit theorem, we're already going to understand the properties of that distribution. So let's talk about central limit theorem in a little bit more detail. Over the long run, each value of a die, if we were dealing with dice, should occur with approximately equal frequency. So we'll use an example with dice to make this point a little bit more clear about central limit theorem. So over the long run, each value, whether it's 1 dot, 2 dots, 3 dots, all the way up to 6, should occur with approximately equal frequency because the die is created in such a way that it's equally weighted. So every single side has one possibility out of 6 of coming up. That would mean that each particular side has a 0.17 or 17% chance of coming up when you roll. If we were to look at a distribution of 1,000 rolls, it would likely look something like this. It'd be relatively flat. You know, it's not going to be perfectly flat. In the real world, we don't find perfect distributions like that. But it's going to be relatively flat where each one of these outcomes, rolling a 1, a 2, all the way up to 6, is going to occur with about 17% probability, 0.17 probability, 17% chance. And then if we were to compute a mean, if we were to take all those times that a 1 came up, all the times that a 2 came up, and so forth, add them all up and compute a mean, we'd probably find a mean somewhere right around here, 3.5. In this particular case, we found a mean of 3.41. And of course, not all the rolls were equal to that mean. Of course, none of them are equal to 3.41 because we can't roll a die and have it come up 3.41. So obviously there's some variability here from that mean, and our standard deviation measures that. Now, according to the law of large numbers, we learned this before, as n increases, in other words, as we roll that die more and more times, the mean of all those rolls should approach essentially the real mean, the true value. And the true value, when we're talking about a mean for rolling a die, is just simply the mean of all the potential outcomes. You could roll a 1, a 2, a 3, a 4, a 5, or 6. If we add that all up and divide by 6, then we should find a population mean equal to about 3.5. And you can see when we rolled that die 1,000 times, our mean was equal to 3.41, which is pretty darn close to 3.5. And according to that law of large numbers, as that sample size increases, as that n increases, we should get closer and closer to that 3.5. So this population of scores right here, it's just simply a distribution of individual scores, individual rolls. I'm going to refer to that as the parent population because it's this parent population of individual scores that we're going to use to create the distribution of sample means. So it's essentially going to give birth to this distribution of sample means. And as I say here, it's really quite romantic, at least from a statistical perspective. So let's talk about that in a little bit more detail. I'll go through an example next of what a distribution of sample means looks like. This is a distribution of individual scores, individual rolls. How does that differ from a distribution of sample means? Let's look at that next. All right, so let's look at this distribution of sample means. And what are we going to do? Instead of graphing results from one roll at a time, we're going to graph means calculated from two separate rolls. So we're going to roll the die once, and then we're going to roll it again. So our n is equal to 2. So just for example, I might roll it once and find a 4. I might roll it again and find a 6. I'm going to compute a mean of those two rolls. 4 and 6 equals 10. 10 divided by 2 equals 5. Well, I can do that over again and over again and over again. And every time I roll the dice twice, I'm going to compute a mean. So right here would be a good example of a distribution of sample means, where you'd have 1,000 rolls of those two die, and I can compute a mean for every single one of those rolling pairs. So every time I roll it twice, I compute a mean, and then I graph what that mean value equals. And we can see here in this case, it forms a pretty characteristic shape that we should be familiar with. The shape is relatively normal. And the mean we can see here is equal to 3.43. It's approaching that mean from that parent population of 3.5. Remember, if I just take a distribution of individual rolls, over the long run, I should expect to find a mean of 3.5, because when I take all the potential outcomes for a roll, finding a 1, a 2, a 3, a 4, a 5, or a 6, if I take a mean of all those potential outcomes, the value that I get is 3.5. So this distribution of sample means that was created based on rolls taken two dice at a time formed a normal distribution, relatively normally shaped, and its mean was pretty close to the mean that we would expect from the parent population. So mu from the parent population was equal to 3.5. Well, let's say now I took 5 dice and I rolled those at the same time, and I computed a mean from all those values. How would that distribution of sample means look? So again, I'm just taking now 5 dice instead of 2. I'm going to add up all those values and divide by 5. So I'm computing a group mean. Well, after 1,000 rolls of those 5 dice, here I can see that the mean is equal to 3.46. So look, I'm even closer than I was before to that true population mean from the parent population of individual scores. And you can also see that the standard deviation is somewhat smaller than what we had when we were rolling 2 die. We have a relatively normal distribution, but it's somewhat tighter. There's less variability. So what we're finding is when we roll 5 dice at once, each sample mean is coming closer to that true mean of 3.5. There's less variability from one roll to the next, from one group mean to the next. Well, what would you expect to find here? Let's say now we're rolling 10 dice. So I'm going to roll those 10 dice, add up all those values, and divide by 10. So again, I'll be graphing group means, but now it's based on 10 rolls at a time. So what we're finding is, as that sample size increases from 2 to 5, what happened? The sample mean came closer to the true population mean, and my variability went down. In other words, every roll, every sample mean that I got from that roll of 10 dice came closer and closer to 3.5. So we should expect a sample mean that's even closer to 3.5 when we look at the distribution of sample means for these 10 rolls, and we should find a standard deviation that's even less. And that's exactly what we find. Here we find that the mean of this distribution of sample means is very close to the mean of the parent population, 3.5. And we see that the standard deviation is really quite small. So when I'm rolling 10 die, it's very likely that I'm going to find a mean very close to 3.5. And it's very unlikely that I'm going to find these means that are very large, very unlikely that I'm going to find these means that are very small. So you see how this is showing me all the possible sample means that I could be finding when I roll 10 dice at a time. Well, we've learned some basic truths here. As our n increases, as our sample size increases from 2 dice to 5 dice to 10 dice, the mean of that distribution of sample means approaches the mean of the parent population, which in this case was equal to 3.5, and the standard deviation of this distribution of sample means decreases as my sample size increases. So it got smaller and then even smaller. And that makes sense, doesn't it? Because now I'm measuring 10 dice at a time. I should be getting a more reliable measurement for every group mean. If I were to roll 20 dice at a time and compute a group mean, that value would be even closer to 3.5, and the standard deviation would be even smaller. So for every 20 dice that I roll, the deviation from 3.5 would be pretty small. I'd usually be getting sample means close to 3.5. All right, well, that's what a distribution of sample means is. Let's just kind of summarize that real quickly. What we found, we were finding that when we just rolled 1 dice at a time, the mean of that distribution was 3.41, and as we rolled it more and more and more times, that mean would get closer and closer to 3.5, because that would be the true population mean based on the law of large numbers. So from that parent population of just rolling it 1 dice at a time, we were able to create a distribution of sample means based on rolling 2 dice at a time, or 5 or 10. And as we rolled more and more dice at one time, the sample mean got closer and closer and closer to that true population mean. And if it was getting closer and closer and closer to the true population mean, that means we would have less variability as our sample size increased. So as we went from 2 to 5 to 10 dice rolling at one time, our standard deviation got smaller and smaller. So this leads us to some various properties regarding central limit theorem. For relatively large samples, we're talking about sample sizes greater than 30. The following should be true. The shape of the distribution of sample means will be approximately normal, and we saw that in the graphics previously. So we already know the distribution of sample means is going to be approximately normally shaped, and that's good because our z distribution is based on a normal distribution. The mean of the distribution of sample means, we often refer to it as the expected mean. That's why you see a little sub e. The mean of the distribution of sample means will approach the mean from that parent population. And we're finding that these means from the distribution of sample means are approaching 3.5. And the standard deviation of the distribution of sample means, which is known as the standard error of the mean. Remember, this sigma right here represents the standard deviation, in a population? Well, when you see a sigma with a sub x bar, now it's representing the standard deviation for the sampling distribution, the standard deviation for the distribution of sample means, and it's often just known as the standard error of the mean. We'll typically just refer to it as the standard deviation. The standard deviation for that distribution of sample means is the standard error of the mean. Well, we're going to be able to compute that by taking the standard deviation from that parent population and dividing by the square root of the sample size. So the bottom line is, according to central limit theorem, I already know that the shape of that distribution is going to be normal. I already know that the mean of that distribution is going to approach the mean that was given from the parent population, and I already know how to compute the variability for that distribution. In other words, we don't need to go through the hard work of constructing it by hand because we already know how it's going to look. We already know its properties. So it's really kind of neat because from that distribution of individual scores from that original population, I already know, particularly if I start with the normal distribution of scores, that that distribution of sample means will be normally distributed like we see in these three graphics right here. And as my sample size gets large, I'll have a normal distribution and it'll be relatively tight. But what's kind of cool about the distribution of sample means is if the parent population is even uniform, like we had in the example with the dice, then the distribution of sample means will still be normally distributed, and as my sample size increases, my standard error will get smaller, and then ultimately, when my sample size is large, I will have a normal distribution that's relatively tight. We can even start off with a skewed parent population of individual scores. When I start drawing multiple scores from that distribution and I graph sample means such that I have a distribution now of sample means, it will become a normal distribution as my sample size increases, and it will be relatively tight, showing relatively small standard errors or standard deviations. So you see, we already know how it's going to come out. And if we already know how it's going to come out, that means that we can save ourselves a lot of time. So armed with this information, we can construct distribution of sample means and then compute probabilities involving those means. Let me show you what I'm talking about. This is the type of thing that after we talk about it conceptually, and it might be a little bit more confusing, once we now start going through examples, it makes more sense. So you have to give me a little bit of leeway, and you have to make sure that you spend some time studying and wrestling with these concepts. But once we start going through actual examples, you'll see that the things should start fitting together. So let's talk about predicting test scores. 8th grade standardized test scores form a normal distribution with a mean of 400 and a standard deviation of 70. Let's say I want to figure this out. What's the probability that one student selected at random will score below 375? Well, as we're moving toward inferential statistics, we're going to need to figure out what's the probability of finding our data just by chance. So we're starting to get close to asking the type of question that we need to ask. What's the probability in this case of finding a student who scores below 375? Now, what we're doing here is what we did back in the previous lecture. We're dealing with just individual scores from a distribution of individual scores. So we're going to go through this example just to remind us of what we're doing, and in the next example we'll be looking at group means. So if I want to figure out this probability of finding a student who scores below 375, we would need to transform that raw score of 375 into a z-score. So I'm going to compute a z-score, which remember is just a standard score, by taking that raw score of 375, seeing how much it differs from the mean of 400, and dividing by the standard deviation of 70. Then we can look that value up in our z-table to compute the probability of scoring so low. So let's go ahead and compute that. We have our formula for z. Z equals our score minus the mean divided by the standard deviation. Our score in this case is equal to 375. We're going to subtract our mean of 400, and then we're going to divide by our standard deviation, which equals 70. So in this case, we're going to have negative 25 divided by 70. Let's use our calculator to figure out what that equals. We'd have 25, I guess we can go ahead and make that negative, divide by 70, that equals negative 0.36, we'll call that. Negative 0.36. All right. Now we're going to need to look up that value in table 5.1. You can open up your book, the back, and check that out. We're going to be using that table a lot. I have that right here. We're looking up a value of negative 0.36. So remember, there's 0. I want negative 0.36. The closest thing that we're going to see is negative 0.35, and we're talking about the 36th percentile. The 36th percentile. So according to that table, a z-score of this value corresponds to the 36th percentile. So that means that there is a 36% chance that a randomly selected student will score below 375. Because remember what those percentiles tell us? If we're in the 36th percentile, it means our score is at or above 36% of the other scores. And we're trying to figure out what's the probability of randomly selecting a student who will score below 375. Well, that value, 375, is at or above 36% of all the other scores. So that's what we did before. That's how we're able to answer that question. But now let's say we're trying to answer that question not based on one randomly selected student, but based on several students who had a group mean of some particular value. So we're going to take this discussion that we had before and extend it to another level based on what we learned about that central limit theorem and the distribution of sample means. Let's go ahead and look at another example. So 8th grade standardized test scores, as we saw before, form a normal distribution with a mean of 400 and a standard deviation of 70. So that's that parent population of individual scores. What's the probability that an entire school of 8th graders, so we're talking about a sample size of 100, will have a sample mean score below 375? So you see how this looks almost exactly how the example looked previously, but we're not talking about an individual score anymore. Now I'm saying what's the probability that an entire school of 100 8th graders will have a sample mean below 375? Can't you see that the probability is going to be much smaller? I mean, now we're not just talking about what's the probability of finding one person who scores 375 or below. Now we're trying to figure out what's the probability that we would select 100 people and find that their mean is below 375. Well, this is now a situation when we are using a modification of computing our z-score. So instead of looking at our raw score, we're looking at our sample mean of 375. We're going to subtract that from that parent population mean of 400 and then divide by the standard error of the mean. Remember, that's just the standard deviation for that distribution of sample means. And the good news is we have formulas for computing those things. So let's go back here to our formula for computing standard error. We know that we can compute the standard error of the mean, sigma sub x bar, by taking the standard deviation from the parent population and dividing by the square root of the sample size. So it makes sense that the distribution of sample means is going to be based on the standard deviation from the parent population because that distribution of sample means was created by that parent population. It should have the same types of characteristics. So we take the standard deviation from the parent population, that was equal to 70. We divide by the square root of the sample size. Square root of, in this case, the sample size is equal to 100. So we've got 70 divided by 10 is, of course, going to equal 7. So that's our standard error in this case when we measure 100 scores. So on average, the sample means will differ from the true population mean by about 7 points on that standardized test. Well, now let's go ahead and compute our z value based on that sample mean. So we're going to take that sample mean, which was equal to 375. We're going to subtract that population mean of 400. And we're going to divide by our standard error, which we just computed, which is equal to 7. Just label that so we don't forget. Okay. So now we've got 375 minus 400, that equals negative 25 divided by 7. Let's compute that real quickly. got 25. We can make that negative and then divide by 7. That equals negative 3.57. Negative 3.57. All right, now we need to look that up. So again, we're trying to figure out what's the probability of scoring below that value. And that's what these percentiles tell us. You can see that we're talking about a really extreme z-score. The most extreme z-score that we have listed in our table is negative 3.5. That's the closest that we're going to find to the negative 3.57. So the percentile 0.02, remember that's much less than 1%. That's 0.02%. The 0.02 percentile. It's a very, very small number. So if we were to write this in, we'd say according to table 5.1, the z-value corresponds to the 0.02th percentile. It's very awkward sounding. The 0.02 percentile. So there is a 0.02% chance that a random sample of 100 students will score below 375. In other words, it'd be very, very unlikely that if we had a distribution of individual scores that had a mean of 400, it'd be very unlikely that we would randomly select 100 and find a sample mean below 375. In fact, it would only happen 0.02% of the time. Now remember, when we're talking about 2%, you're talking about 0.02. That equals 2%. 0.02% would be 0.0002. That's 0.02%. So just to give you a sense of how rare it is, 2% would be 2 times out of every 100. Here we're talking about the tenths place, hundredths place, thousandths place, 10,000ths place. That's 2 times out of every 10,000 would we expect to find a sample mean below 375 when we're measuring 100 students. It's very unlikely. And the distribution of sample means was able to help us figure that out, given what we know about central limit theorem. Let's go through another example. This one is actually just showing you what we just did. It's a little bit easier to read. I know sometimes it's hard to read what I write. This is just to make sure that you've got it in your notes very clearly. Now let's go through another example. Salaries at a company of 9,000 employees form a normal distribution with a mean salary of $26,400 and a standard deviation of $2,420. Upholster samples 400 random employees and finds a mean salary of $26,650. All right. Is it likely to find this discrepancy by chance? Because remember, this is the real answer, 26,400. If we randomly select 400 people, is it likely that we'd find this difference between 26,650 as the mean salary that we compute based on those 400 people? Or, is it likely or is it very unlikely that we would find a difference between 26,650 and 26,400? That seems like a really small difference, doesn't it? Well, remember, we measured 400 people though. So if we're measuring 400 people, every sample mean that we compute is probably going to come pretty darn close to 26,400. So what's the probability that we'd find this big of a difference just by chance? See, we're getting really close to exactly the type of question that we ask when we do inferential statistics. Because when we say we have statistically significant results, we're essentially saying that we have effectively ruled out finding our data just by chance. So I need to figure out what's the probability of finding differences between these values just by chance. This seems like such a small difference, but I'm telling you, when you measure 400 people, you shouldn't expect to find very big differences just by chance. So let's compute it. Let's go ahead and compute our standard error first. So our standard error is going to equal our standard deviation from the parent population. That was equal to 2,420. And we divide by the square root of our sample size. Square root, in this case, of 400 as our sample size. Okay, let's just simplify and solve it. We've got 2,420 divided by, let's figure out the square root of 400. So we'll take 400 and hit the square root key. That equals 20. I guess I should have been able to do that in my head. Equals 20. Now we're going to need 2420 divided by 20, and that's going to equal, let's see, 2420 divided by 20 equals 121. So our standard error of the mean, which is just the standard deviation for that distribution of sample means, equals 121. So here's one thing to keep in mind too. The standard error of the mean works just like a normal standard deviation. Remember that empirical rule? Within one standard deviation of the mean, 68% of all scores will fall. Well, within one standard error above and below the mean, we should find 68% of all sample means. So within one standard error above and below the mean, 68% of all sample means will fall. You'll see there's not much variability that we expect from one sample to the next when we have a sample size of 400. Well, we needed to compute the standard error before we could compute z. So next, let's compute z. Let me just label that again, just so we don't forget. Let's now compute z. We're going to take our sample mean, which was equal to 26,650. 26,650. And then we're going to divide, we're going to subtract our population mean, which is 26,400. 26,400. Let me just extend that. And now we're going to divide by our standard error, which we just computed, which was equal to 121. Okay, when we take 26,650 and then we subtract 26,400, you can see that we get 250. And when we divide by 121, let's use our calculator to figure that out. 250 divided by 121 equals 2.07. It looks like we can call that 2.07. All right, that's a relatively large z-score. So what we're going to need to do is look that up in our z table. So how rare of a z-score is that? Here's a z-score of 0. We're looking for 2.07. That's 2.07 standard errors above the mean. Remember, that's pretty far out there. Within 2 standard errors above and below the mean is 95% of all sample means. This is even beyond that, 2.07. Well, here's 2. Here's 2.1. That's the closest thing that we have to 2.07. We're talking about the 98th percentile. Okay. So this z value corresponds to the 98th percentile. So the mean salary of this particular sample is greater than 98% of all possible samples of 400 employees. In other words, that's a really high mean that we found just by chance. It's greater than 98% of all sample means that we would find when we're sampling 400 people. So it's really quite high. Here is everything worked out where it's just a little bit easier to read. If you missed something because of my writing, you can see it a little bit more clearly. And what might be our interpretation of the results? The sample mean is very high, suggesting that maybe the survey was flawed. It doesn't seem to be doing a really good job, as well as we would expect, of capturing that population mean based on that sample of 400 people. I think that's fascinating that we would find a difference between 26,650 and 26,400, finding that difference is so unlikely, even though it really looks like they're pretty close in terms of the values. So what we've learned here is we really can now quantify what's the probability of finding the data that we have found just by chance. And that's exactly what we're going to need to do the next time we get together and talk about inferential stats. So I know this has been kind of a tough road to go down. We're learning a lot of complicated things here, but you are right now going through some training so that you can learn the basic skills necessary for doing inferential stats. And I'm happy to say that we're pretty much at that point now. So the next time we get together, we're going to learn some really neat stuff with hypothesis testing and inferential stats. Well, that was the key concepts from section 5.3. So for now, that is all.